A critical aspect of algorithms in computer science is the question of how much work do they do? How efficient are they? It's kind of related to the question of how fast do they run, except we often don't care about exactly how fast they run because that varies by computer. If you run them on a slow computer, they take a long time. If you run them on a fast computer, they go faster. But we do care about the amount of work, and we want to know something about how that amount of work is going to grow as the inputs grow. And this is what we refer to as order analysis. For this, we typically pick some operation, something that's kind of critical to whatever it is that we're doing, possibly a family of operations, and we count how many times these operations would happen for a random input of a given size. And that tells us basically how much work the algorithm is going to do. And a lot of times what we're interested in is how it's going to scale as the input gets larger. So let's talk about this for our sorts. We'll start off with bubble sort. So our array, let's say it has n values in it. We have n values in our array. Actually, I'll go with a lowercase n. And the question is, well, how much work does bubble sort do? Well, there are different things that we could count here. In the case of sorting, there are two main things we want to count. Either we want to count the comparisons, how many times we do a less than or greater than, or we want to count kind of the memory moves, the swaps, how many times we do those. In the case of bubble sort, it doesn't really matter, other than at least the comparisons are easier to talk about in the sense that we always do the same number of them. Depending upon the data itself, we might do fewer or more swaps. For example, if everything was in order to start with, we'd never do any swaps. So we're going to start by focusing on comparisons. So how many comparisons are done when we try to sort n values? Well, let's look. So the first time through this loop, this loop is going to happen n minus 1 times. So n minus 1. The second time through the loop, I will, instead of being 0, will be 1, so it'll happen n minus 2 times. And every time through that inner loop, one comparison occurs. The next time is n minus 3. The next time is n minus 4, and you can see where this is going. We'll get down to, we do 2 comparisons, and 1, etc. So what is this summation? Well, turns out that that sum can be nicely expressed as n times n minus 1 divided by 2, which happens to be equal to n squared, quantity over 2, minus n over 2. And when we talk about the order of this, what we typically do is we throw away everything but the largest term here. In fact, we even throw out constants. Because like I said, we care about how things scale. So it turns out that bubble sort does comparisons in a way that we refer to as order n squared. So the size of our array, the number of comparisons that we do, grows with that value squared. And of course that's determined by this first term right up in here. What about sorts, or the swaps in there? Well, it turns out that if the thing is completely out of order, so if it was in the wrong direction completely, this would also be exactly this expression. If it's random data, you can almost expect that it's going to do half as many. But because we throw away these constant multipliers, in this case we have a constant multiplier of a half, we throw those out. Because what we care about is the fact that if I double the size of the input, if this is n squared, when I double the input size, it's going to do 4 times as much work. We're definitely going to do 4 times as many comparisons. If the data is random, we might do half as many swaps as we do comparisons, but it's still going to be 4 times as much as it was for a data set that was half the size. So our bubble sort is what we call order n squared. What about our min sort? Well, it turns out we have the same structure here. We have a for loop that goes n minus 1 times, and we have an inner loop that the first time it goes n minus 1 times, and the next time it's n minus 2, n minus 3. Same thing happens here for the comparisons. So inside of here, we're doing a comparison between our array values, but note that we never move values around in the array inside of the min sort. So for the min sort, if the operation that we're counting is comparisons, just like the bubble sort, it's order n squared. And in fact, the math all works out exactly the same. But min sort only does order n swaps. This outer loop happens n minus 1 times. This swap is inside of the outer loop, it's not inside of the inner loop, so it happens n minus 1 times, and n minus 1 is order n. Because once again, we throw away everything but the highest term, and we would throw away any constant multipliers on there as well. So the min sort can be very good if this was an expensive operation. Now, in the case of what we're dealing with, it's not. Pretty much nothing that we will do in Scala will have this being a more expensive operation than the comparisons, at least not by much, but the min sort can be faster for certain things by a significant amount because its order for the swapping is distinctly lower. What about insertion sort? In some ways, this one's the hardest to analyze because this while loop can break out at any point. In fact, that's the whole advantage of insertion sort. Once again, if we start with random data, our outer loop is going to happen n minus 1 times. This inner loop, if it went as far as it could, so in our worst possible case, it's actually going to do just as much work. But instead of starting with n minus 1 plus n minus 2, the first one gets pushed back 1, the second one gets pushed back 2, the next one gets pushed back 3, up to n minus 1. So we would have the same sum that we have here, it's just in the opposite order. Of course, addition is commutative, so it doesn't matter. And we would do exactly as much work in the worst case. Turns out that on average, though, the insertion sort, this while loop only goes halfway through, and so instead of these being n squared over 2 and n over 2, on average for the insertion sort it's divided by 4 in both cases, but that's still order n squared because the order only cares about how it's growing for large inputs. So all three of these sorts are fundamentally order n squared sorts. You double the size of your input, it's going to take 4 times longer. If you are sorting 10 times as much data, it's going to take 100 times longer. And therefore these don't necessarily work that well for really large input sets. Now, for certain things, order n squared would be considered great. It's actually a fairly low order polynomial. It just so happens that we can do better for sorting. In the case of sorting, we can make data sets that are large enough that these will run slow, and we want to try to do something better. This whole concept of order, we'll come back to it when we start talking about searching for things, and it really is a critical aspect in computer science. You kind of want to get a feel for being able to think about the order of algorithms, because that tells you a lot about how they're going to perform as your inputs get large.